Section 1.2 Adding and Subtracting Whole Numbers. In this video we will learn how to add and or subtract whole numbers with the commutative property of addition, grouping symbols, the associative property of addition, the additive identity, larger whole numbers, order of operations, and applications of geometry and alternative fuels. Section 1.2 Adding and Subtracting Whole Numbers. In the expression 3 plus 4, the whole numbers 3 and 4 are called addends or terms. We can use a visual approach to find the sum of 3 and 4. First, construct a number line as shown in Figure 1.2. Start at the number 0, then draw an arrow 3 units to the right. This arrow has magnitude length 3 and represents the whole number 3. Draw a second arrow of length 4, starting at the end of the first arrow, representing the number 3. This arrow has magnitude length 4 and represents the whole number 4. The sum of 3 and 4 could be represented by an arrow that starts at the number 0 and ends at the number 7. However, we prefer to mark this sum on the number line as a solid dot at the whole number 7. The commutative property of addition. Let's change the order in which we add the whole numbers 3 and 4. That is, let's find the sum 4 plus 3 instead. As you can see in Figure 1.3, we start at 0, then draw an arrow of length 4, followed by an arrow of length 3. However, the result is the same, i.e., 4 plus 3 equals 7. Thus, the order in which we add 3 and 4 does not matter. That is, 3 plus 4 equals 4 plus 3. This property of addition of whole numbers is known as the commutative property of addition. Let a and b represent two whole numbers. Then in general, a plus b equals b plus a.
Grouping symbols. In mathematics, we use grouping symbols to affect the order in which an expression is evaluated. Whether we use parentheses, brackets, or curly braces, the expression inside any pair of grouping symbols must be evaluated first. For example, we would add 3 to 4 and 7 to 5 to get 12. The rule is simple. Whatever is inside the parentheses is evaluated first. Note, when writing mathematical statements, follow the mantra, one equal sign per line. This will make it much easier to follow your work. We can use brackets instead of parentheses, like in the following example. Add 7 to 9 to get 16, and then 5 to 16 to get 21. Again, note how the expression inside the brackets is evaluated first. We can also use curly braces instead of parentheses or brackets. Add 2 to 3 to get 5, then 5 to 4 to get 9. Again, note how the expression inside the curly braces is evaluated first. If grouping symbols are nested, we evaluate the innermost parentheses first. For example, first add 4 to 5 to get 9. Then evaluate within brackets by adding 3 to 9 to get 12, then 2 to 12 to get 14. Grouping symbols. Use parentheses, brackets, or curly braces to delimit the part of an expression you want evaluated first. If grouping symbols are nested, evaluate the expression in the innermost pair of grouping symbols first. The associative property of addition. Consider the evaluation of the expression. We evaluate the expression in parentheses first, add 2 to 3 to get 5, and 5 to 4 to get 9. Now, suppose we change the order of addition to grouping 3 and 4 instead of 2 and 3. Then we would evaluate by adding 3 and 4 first to get 7, then 2 to 7 to get 9. Although the grouping changed, the result is the same. That is, grouping 2 to 3 is equal to the expression with 3 and 4 group. This property of addition of whole numbers is called the associate property of addition. We let a, b, and c represent whole numbers. Then, whether we group a and b or b and c, the two expressions are equal.
The additive identity. Imagine a number line visualization of the sum of 4 and 0, i.e. 4 plus 0. In Figure 1.4, we start at 0, then draw an arrow of magnitude, length, 4, pointing to the right. Now, at the end of this arrow, attach a second arrow of length 0. Of course, that means that we remain right where we are at 4. Hence, the shaded dot at 4 is the sum. That is, 4 plus 0 equals 4. And so we have the additive identity property. The whole number 0 is called the additive identity. If a is any whole number, then a plus 0 equals a. The number 0 is called the additive identity because if you add 0 to any number, you get the identical number back. Adding larger whole numbers. For completeness, we include 2 examples of adding larger whole numbers. Hopefully, the algorithm is familiar from previous coursework. Example 1. Simplify 1,234 plus 498. Solution. Align the numbers vertically, then add, starting at the furthest column to the right. Add the digits in the ones column. 4 plus 8 equals 12. Write the 2, then carry a 1 to the tens column. Next, add the digits in the tens column. 3 plus 9 equals 12. Add the carry to get 13. Then write the 3 and carry a 1 to the hundreds column. Continue in this manner, working from right to left. Therefore, 1,234 plus 498 equals 1,732. Add 3 or more numbers in the same manner. Example 2. Simplify 256 plus 322 plus 418. Solution. Align the numbers vertically, then add, starting at the farthest column to the right. Add the digits in the ones column. 6 plus 2 plus 8 equals 16. Write the 6, then carry a 1 to the tens column. Continue in this manner, working from right to left. Therefore, 256 plus 322 plus 418 equals 996. Subtraction of whole numbers. The key idea is this. Subtraction is the opposite of addition. For example, consider the difference 7 minus 4 depicted on the number line in figure 1.5. If we are adding 7 and 4, we first draw an arrow starting at 0, pointing to the right with magnitude, length 7. Then, to add 4, we would draw a second arrow of magnitude, length 4, attached to the end of the first arrow and pointing to the right. However, because subtraction is the opposite of addition, in figure 1.5, we attach an arrow of magnitude, length 4, to the end of the first arrow, but pointing in the opposite direction, to the left. Note that this last arrow ends at the answer, which is a shaded dot on the number line at 3. That is, 7 minus 4 equals 3. Note that subtraction is not commutative. That is, it makes no sense to say that 7 minus 5 is the same as 5 minus 7. Similarly, 7 minus 4 is not the same as 4 minus 7. Subtraction is also not associative. On the one hand, grouping 9 and 5, 9 minus 5 is 4, minus 2 equals 2. If we group 5 minus 2, then we get 9 minus 3 equals 6. 6 and 2 are not the same answers. So subtraction is not associative. Subtracting larger whole numbers. Much as we did with adding larger whole numbers, to subtract 2 large whole numbers, align them vertically, then subtract, working from right to left. You may have to borrow to complete the subtraction at any step. Example 3. Simplify 1,755 minus 328. Solution. Align the numbers vertically, then subtract, starting at the ones column, then working right to left. At the ones column, we cannot subtract 8 from 5, so we borrow from the previous column. Now, 8 from 15 is 7. Continue in this manner, working from right to left. Therefore, 1,755 minus 328 equals 1,427. Order of operations. In the absence of grouping symbols, It is important to understand that addition holds no precedence over subtraction and vice versa. Perform all additions and subtractions in the order presented, moving left to right. Let's look at an example. Example 4. Simplify the expression 15 minus 8 plus 4. Solution. This example can be trickier than it seems. However, if we follow the rule, perform all additions and subtractions in the order presented, moving left to right, we should have no trouble. Caution! Incorrect answer ahead. Note that it is possible to arrive at a different but incorrect answer if we favor addition over subtraction in example 4. If we first add 8 and 4, then 15 minus 8 plus 4 becomes 15 minus 12, which is 3. However, note that this is incorrect. Because it violates the rule, perform all additions and subtractions in the order presented, moving left to right. Applications: Geometry. There are any number of applications that require a sum or difference of whole numbers. Let's examine a few from the world of geometry. Perimeter of a polygon. In geometry, a polygon is a plane figure made up of a closed path of a finite sequence of segments. The segments are called the edges or sides of the polygon, and the points where two edges meet are called the vertices of the polygon. The perimeter of any polygon is the sum of the lengths of its sides. Example 5. A quadrilateral is a polygon with 4 sides. Find the perimeter of the quadrilateral shown below, where the sides are measured in yards. Solution. To find the perimeter of the quadrilateral, find the sum of the lengths of the sides. Perimeter equals 3 plus 3 plus 4 plus 5 equals 15 yards. Example 6. A polygon with 4 sides is a rectangle if all 4 of its angles are right angles. It can be shown that the opposite sides of a rectangle must be equal. Find the perimeter of the rectangle shown below, where the sides of the rectangle are measured in meters. Solution. To find the perimeter of the rectangle, find the sum of the 4 sides. Because opposite sides have the same length, we have 2 sides of length 5 meters and 2 sides of length 3 meters. Hence, perimeter equals 5 plus 3 plus 5 plus 3 equals 16 meters. Example 7. A quadrilateral with 4 sides is a square if all 4 of its sides are equal and all 4 of its angles are right angles. Pictured below is a square having a side of length 12 feet. Find the perimeter of the square. Solution. Because the quadrilateral is a square, all 4 sides have the same length, namely 12 feet. To find the perimeter of the square, find the sum of the 4 sides. Perimeter equals 12 plus 12 plus 12 plus 12 equals 48 feet. Application: Alternative fuels. Automobiles that run on alternative fuels other than gasoline have increased in the United States over the years. Example 8. Table 1.2 shows the number of cars in thousands running on compressed natural gas versus the year. Create a bar chart showing the number of cars running on compressed natural gas versus the year. Solution. Place the years on the horizontal axis. At each year, sketch a bar having height equal to the number of cars in that year that are running on compressed natural gas. Scale the vertical axis in thousands. Example 9. Using the data presented in Table 1.2, create a table that shows the differences in consecutive years, then create a line plot of the result. In what consecutive years did the United States see the greatest increase in cars powered by compressed natural gas? Solution. Table 1.3 shows the differences in consecutive years. Next, craft a line graph. Place consecutive years on the horizontal axis. At each consecutive year, plot a point at a height equal to the difference in alternative fuel vehicles. Connect the points with straight line segments. Note how the line graph makes it completely clear that the greatest increase in vehicles powered by compressed natural gas occurred in the consecutive years 1996 through 1997, an increase of 13,000 vehicles.